I'm chairing the session on behalf of Folake, who had to leave. My name is Elodie, and I'm secretly working for the MAPS project. And I'm happy to chair this session on behavioral research. So we have 6 presenters, and five of them are online. We'll start with Anna Diakonu, who is from University of Montreal, and she's online. Please, Hannah, the floor is yours. You have 10 minutes. Hello.
Hi, I assume you all can hear me now. So I'm presenting today integrating behavioral elements into agriculture and nutrition linkages using evidence from Ecuadorian farmers, along with my co-authors from Université de Montréal. So as many of you know, agriculture for nutrition interventions benefit from frameworks that help understand the complexities of the pathways connecting production and consumption, like this framework that I'm a big fan of. And using agriculture for nutrition outcomes in large part comes down to focusing on what people grow, what they sell, what they buy, and what they eat. These frameworks are very rational and instrumental, but ultimately it's humans who are conducting the behavior. And as humans, we are not always so rational. I know of times that I've eaten something that was pretty bad for me, even though I had the knowledge that it was bad for me. I had physical access to a healthier option, and I had the money to pay for a healthier option. But in the moment, I was motivated by, say, taste or peer pressure or convenient packaging more so than by nutrition. This quote-unquote irrationality of human behavior leads to some issues in attempts to define clean pathways. Some of you are probably familiar with the body of research that quantifies the relationship between agricultural diversity and dietary diversity. Mostly, this literature looks at the linkages that are shown on this slide. If the relationship between production diversity and dietary diversity were perfect, any increase in production diversity would result in an equal increase in dietary diversity. But several reviews on the subject have concluded that while most studies do find a positive relationship between production and dietary diversity, the size of the relationship is really quite small and maybe even a bit disappointing. And part of this is certainly due to methodological issues in some of the studies, like when production diversity is measured for the year, but dietary diversity is measured for only a day. But we suspect that there's an additional reason for the small association, which is that there are behavioral components that are just not captured by these studies. Luckily, there's a field of research around human behavior that can help us out. This is the COM-B model, which states that capabilities, motivations, and opportunities coalesce to form behaviors. This is one of the leading behavioral models today, and we thought it could shed some light on agriculture and nutrition linkages. For example, we find that agriculture and nutrition frameworks give a lot of attention to capabilities and opportunities, but tend to imply that income and own consumption are the only motivations. So in our research, we wanted to add a little bit of nuance there. The research I'm presenting today is part of a bigger mixed method project on agriculture nutrition linkages in Ecuador, titled Evaluating and Bringing to Scale Alternative Food Networks to Address Diabetes Mellitus and Hypertension. This project has a number of objectives and methods involved, but today I'll focus on our objective of using a behavioral perspective to better understand farmers' agriculture and food practices. To do this, we used activity-based interviews like in this picture, and we oriented these according to elements from the COM-B model as well as agriculture nutrition pathways. A main activity in the interviews was a pile sorting technique, which we designed to get at the motivations behind farmers' production diversity of both plants and animals. So in a first step of the pile sorting, participants sorted out the cards that represent the plants they grew and the animals they raised in the past year, even if they only had a small amount or if it didn't successfully bear fruit. Next, they further separated their selection of plants and animals according to the ones that they consumed a lot of from their own production and the ones they consumed a little of or not at all from their own production. They did this for both plants and animals. And then, again, for both plants and animals, they identified motivations other than own consumption for the plants they grew and the animals that they raised. And finally, they categorized the plants and the animals into the motivations with the ability to place each product into as many motivations as they wanted. So here below, you can see the motivations that one farmer came up with for raising his animals and the animals that he put into each of those motivations. So this method allowed us to, first of all, get a sense of the plant and animal diversity on people's farms. And it showed us that for both plants and animals, consumption was divided about 50-50 between the products that they consumed a lot of and the ones that they consumed little or not at all of from their own production. And so if only half the products are consumed frequently, it makes us want to better understand, what is this other half destined for? Looking at the motivations can help us understand that. We examined what motivations people came up with as well as their relative importance. We did this through a weighted score in which we took the number of times that a motivation was brought up and we multiplied that by the proportion of their total products, the total products that were assigned to that motivation in the pile sort. So what we see here is that for growing plants, other than own consumption, commercial sales is a very important motivator, just as we might have expected. The next strongest is the category of social motivations, in particular, using diversity as a means to engage in barter, in gifting, or certain cultural exchange practices and social events. Next, we have agronomic motivations, which mostly has to do with the role that diversity plays in supporting the farm ecosystem. And last, I'll point out the affective category, which has to do with the sentimental aspects, the joy, the beauty, and the cultural connection that people find in growing diversity. And when we turn to animals, we find that the motivations are a little bit different. And again, just a reminder that these are motivations other than own consumption. So here, the agronomic motivations are by far the most important, in particular for the contribution that animals can make to soil fertility through their manure. The affective motivations came in second, which in this case has to do not just with the joy of raising farm animals, but also with the sense of companionship. The commercial motivations are right up there with affective, and then they're followed by social and finally medicine and security. Now, if we return to our links between production diversity and dietary diversity, we can plug in our motivations here in orange, which include agricultural sales and own consumption, as well as the other motivations we identified in this research. And these motivations act on production diversity as a behavior, but actually it's a two-way street because these motivations are essentially the destinations of the diversity itself. We found this exercise to provide some clarity on why the measured relationship between production diversity and dietary diversity is not always very strong, as there are all these other uses for production diversity that can essentially muddle the waters in statistical analyses. But more importantly, we found this research to provide interesting avenues for supporting agricultural diversity. While many of the motivations we found are not directly linked to nutrition, they might still play an indirect role in supporting nutrition. So to explain this, I'll give the example of a farmer in our study area. This farmer in this picture grows an immense diversity of varieties of corn. As we all know, seed diversity is important for farmers' food security and nutrition in many ways. It improves resilience in the face of pests or extreme climate events, it extends the harvest season, and it provides a greater diversity of nutrients. But none of those were the reasons he expressed for his immense diversity. His reason was that his community holds a competition on who has the greatest variety of corn seeds, and it's a point of pride for him to do well in that competition each year. His story suggests that paying attention to affective components like pride can be very important in efforts to promote agricultural diversity. So by recognizing that farmers are driven by many motivations, we can better mobilize them to support agricultural diversity. Here, I think it's worth pointing out that agricultural diversity is not just useful for dietary outcomes, but also to replenish the soil, support the farm's productivity, and provide ecosystem services to the surrounding environment. But a bunch of questions remain on what the more specific links between these complex motivations and human health look like. In answering these questions, it is important to remember that farmers' motivations are just one part of what forms behaviors, and also that farmers' behaviors are just one part of our efforts to create healthier food systems. Our intention with this research was to give greater protagonism to behavioral elements within agriculture nutrition frameworks, like the one we saw at the beginning of the presentation. And this is with the hope of adding just a humble little piece to the complex understanding needed to transform food systems for better health. Thank you very much.
Thank you, Hannah, for this presentation and this insights into the motivations of the farmers. So, thanks for joining us online. So our next speaker is Nikki Joshi from Patnagar.
So hi, I'm Nikki Joshi from GB Pant University of Agriculture and Technology, Patnagar, presenting a paper titled Association of Food Choice Motives with Health Status and Dietary Environmental Footprints in India. Sustainability concerns are raised for the current food systems, and our food choices can potentially make these food systems sustainable. Our food choices are shaped by a number of factors such as personal, psychological, social, socioeconomic, contextual, and cultural factors. And food choice motives are psychological attributes that informs our food decisions, our behavior, and preferences. No research has directly examined the influence of food choice motives on health status and dietary sustainability. Therefore, we address this gap by aiming to measure the food choice motives of Indian adults and their association with health status and dietary environmental footprints. For this, we conducted an online cross-sectional survey among Indian adults aged 18 years and above using a convenient sampling technique. The sample size was 930 respondents, and here the map shows the responses obtained from the various parts of the country. Food choice motives were assessed using food choice questionnaire. The motives related to convenience, weight control, health, natural content, mood, price, sensory appeal, familiarity, ecological welfare, and religion were explored. Besides this, information on self-reported body weight, height, blood sugar, and blood pressure was collected. Perceived stress scale and physical activity questionnaire was used to collect data on stress and physical activity levels, and we use semi-quantitative food frequency questionnaire to collect the dietary data. Association of food choice motives with health status and dietary environmental footprints was investigated. Multiple linear regression was run to predict whether food choice motives can independently predict the body mass, blood sugar, blood pressure, perceived stress, physical activity, and dietary environmental footprints like greenhouse gas emissions, green and blue water footprint, and land use footprint. If we see the health status of the respondents, we found that 30.2% were overweight, about 4.9% were hypertensive, and 20.3% reported higher levels of random blood sugar. About respondents, mostly respondents were moderately stressed and reported moderate levels of physical activity. If we see the dietary environmental footprints of the current sample, greenhouse gas emissions from the daily diets were 4.42 kg CO2 equivalents per day. Green and blue water footprint were 3.94 cubic meter and 0.84 cubic meter per day respectively. And the land use footprints of the daily diets were 9 meters squared. We found that health was the most important motive influencing the food choices of the respondents in the current study, followed by natural content and the motive of ecological welfare, while the least important motive influencing the food choices was convenience, and followed by familiarity with their food choices and the religious values. Through linear regression, we found that importance of weight control motive in the diet predicted higher body mass index and higher blood pressure levels with reduced blue water footprint. Giving importance to sensory appeal in dietary choices increased the levels of random blood sugar levels. We found that perceived stress was negatively associated with natural content and the motive of ecological welfare, while it is positively associated with the price motive. So we can see that the respondents who are giving importance to the natural content and ecological welfare in their diet have reduced levels of the stress, and those giving importance to the price motive increase their stress levels. Importance of ecological welfare in the food choices increase the levels of physical activity, and at the same time it reduced the dietary greenhouse gas emissions and the land use footprints. So, at the end of the study, we conclude that the food choice motives impact the health status and dietary environmental footprints. Food choice motives, shaped by the health awareness and environmental education, can contribute towards the food system sustainability by reducing the burden of lifestyle disorders and environmental footprints of the diets. We want to thank all the study participants for their cooperation, and the Senior Research Fellowship to the first author from the University Grand Commission, New Delhi, is duly acknowledged.
Thank you, Nidhi, for this presentation and for keeping on time. And now we are moving to the next presenter. So he's Ryan
Thank you.
Moore from Tufts University, he's online as well.
Hi, everyone. Again, I'm Ian from Tufts, and I'll be presenting today on improved wash practices and reduced water contamination through a social behavior change program in Agago District, Uganda. So this comes from the One Nutrition in Complex Environments study, which evaluated 2 social behavior change programs, which were both 12 to 14 weeks long, and they were intended to be gendered, multi-level, multi-sectoral, and community-based interventions aimed at reducing malnutrition. The first is the NIP program, which is a traditional WASH intervention. And the second is the NIP Plus program, which has everything that the NIP program has, plus additional modules on water assessment and water quality management. The 2 outcomes I'll be presenting on today are WASH knowledge and practices, as well as water contamination. And this is a collaboration between Tufts as well as USAID, Goal, CEMET, and Cornell. So again, this is in Agago district of northern Uganda, and the specific counties in the study are shown in blue on the right here. So the NIP program also included other non-WASH modules, but 2 main WASH modules were related to WASH practices and construction of hand washing stations and construction of improved latrines, which were not paid for, but demonstrations were made. So NIP Plus again included all modules in the NIP program, as well as these additional modules. And in terms of WASH specifically, they were related to water testing and water management. So I'll be presenting on 2 time points. The baseline was pre-intervention, which was, and data for this time point was collected between March and April 2021, and inline post-intervention, which was collected July through October of 2021. The full sample was 900, and for the knowledge and practices, and the subsample for water contamination was 360. In the end, we ended up with 275 households in NIP, 284 in NIP Plus, and 285 in control. So our first research question is, did the NIP and NIP Plus interventions improve WASH knowledge and practices? And the answer is yes. So I'll get into some of these results here. First, we'll be looking at water treatment and type of water treatment by intervention arm at baseline and inline. So we see by the bar graph on the left here that at baseline, really no households across all arms were treating their water. And at inline, we see that NIP increased to 9% of households, and NIP plus increased to 26% of households. And most of that water treatment is boiling, in the form of boiling, shown by the pie charts here. In adjusted regression results, using generalized linear models, we see that NIP households have 7.8 times higher probability of treating water, and NIP plus have 23 times higher probability of treating water compared to control. In terms of hand washing facility use, we see that it's similar across, but non-zero, close to 10 to 20% across all arms at baseline. That moved up significantly at inline for NIP and NIP plus. And the proportion using soap and water also was much higher for NIP and NIP plus. And again, we see that NIP households have 5.5 times higher probability of having a hand washing facility, and NIP plus has 6.5 times higher probability compared to control. Our second research question is, did these interventions reduce risk of household water contamination? And the answer here is yes, in terms of NIP plus. So these are unadjusted results for baseline and endline, showing that the percentage contaminated at baseline here in green was similar across arms at baseline. We saw an increase in control to inline, and a slight increase, a non-significant increase in NIP plus to inline, NIP, to inline, and NIP plus stayed about the same. More importantly, here are adjusted regression results showing that the effect estimate here, the relative risk for NIP, is not significant, but is significant for NIP plus. And NIP plus households had 25% lower risk of E. coli contaminated household water at inline compared to control. And these were regression models adjusting for cluster sampling, as well as many other socioeconomic factors. This was a randomized control trial as well. So our key takeaways here are that the NIP plus intervention increased wash knowledge and practices, and reduced risk of household water contamination in terms of E. coli contamination. And the NIP intervention increased knowledge and practices, but did not significantly reduce risk of contamination. And even with these interventions, NIP and NIP plus, the prevalence of water contamination remains high at about 50%. So question remains, how much more reduction in contamination can be achieved through social behavior change interventions without addressing structural, institutional, or environmental challenges? I'd like to thank our full study team here, Goal Uganda, CIMMYT, Cornell University, and here at Tufts, including our PI, who I believe is in the audience, Shivani Ghosh, all of our participants in Agago District, our volunteers from the communities, as well as USAID. And this presentation was made possible through USAID, but the opinions of authors, including myself, do not reflect the views of the agency. And thank you very much.
Thank you, Ian, for joining the session online. The next presenter is Hélène Harris-Fry from London School, and she's online. So, Hélène, you have 10 minutes.
Hi, thank you so much for having me. I will present with as much enthusiasm and energy as possible. This afternoon, I'll be talking about the potential health gains that could be achieved through dietary change. And this project is motivated by the problem of a rising co-prevalence of undernutrition, overweight, and micronutrient deficiencies. And that comes together to be a problem called the triple burden of malnutrition. And whilst we can find this triple burden throughout the world, it's much more serious in some places than in others. Take this map, for example. The orange shaded areas indicate countries where the triple burden is particularly high. But beyond these country-level inequalities, there are wide inequalities within countries and even within households. A multi-country study has shown that around half of all BMI inequality occurs within households. Diets play a hugely important role in this, and modelling studies have told us that increasing intakes of fruits, vegetables, and whole grains, whilst reducing intakes of unhealthy foods, could substantially improve health outcomes worldwide and save lives. And if we piece this together, we can imagine that households could improve their health by first choosing and then allocating foods in a different way. And that's what behaviour change interventions aim to do: nutrition education counselling, food package labelling, food-based dietary guidelines. But so far, these interventions have all been only modestly successful unless they're also paired with interventions that aim to improve and increase budgets. And so that leaves the question, is this because poor families can't afford to follow the dietary advice? Or is it because behaviour change interventions are badly designed, or diets are just simply hard to change? This analysis aims to answer this question by estimating the maximum potential gains that could be achieved by changing dietary household behaviours. And we do this in a two-stage approach. The first is by optimising food choice with locally available foods, and then optimising the allocation of those foods to household members. We then apply this to a detailed dietary data set collected in rural Bangladesh by IFPRI, and many thanks to IFPRI for sharing these data. So in this first stage of optimising food selection, we solve this using a linear programme where the objective is to maximise the micronutrients available to the household. So in this equation, the one at the top is QK, denotes the quantity of food that the household would buy, and that's the decision variable that we're solving for. And that's based on the concentration of nutrients in each food, that's the blue bit at the top, and that's scaled by the requirements for the household, that's the red bit at the bottom. Now, all of this is subject to a set of constraints. Firstly, really importantly, it ensures that the chosen basket of foods exactly meets the energy needs of the household, so there's no surplus and there's no deficiency. And the second ensures that the price times the quantity is within the household's budget, so they can afford to buy that set of foods. And the remaining constraints ensure that the quantities of foods chosen in this optimal solution are within sensible upper and lower limits. Now that we've done that, we need to optimize the allocation of nutrients available to each household member. And to do this, we maximize the sum of nutritional health in the household. So we maximize the sum of nutritional health for each household member, where health is a function of the quantity of nutrients consumed, that's the Q, subject to their requirements, that's the R. But we weight this sum with lambda here, and this lambda is, we set that now as 1 divided by the number of households in the number of members of the household. So effectively what that weight is saying is that we're not prioritizing the health of any one particular member over another member. Now, to solve this problem, we need to replace that general function, that general health production function, with something more specific that's a parameterized function that actually tells us how intakes relate to health outcomes. And this is the tricky bit. I'll start with energy. What we need is an inverse U-shaped relation between energy intake and health. And that means that the unconstrained optimal solution avoids deficiency and it avoids excess. Then the quantity, QE, is the quantity of energy intake subtracted their energy requirements to give energy balance. And that's the top green bit of the equation. And if we view that as deviations from a healthy weight, since weight loss and weight gain are linear functions of energy balance, we then divide this by body weight squared. So effectively what this numerator and denominator come together to give us are deviations from a healthy BMI. Then we assume, based on a study of 230 cohorts, that mortality risk from BMI is a quadratic relation. And so that's the squared term up at the top there. So really what this gives us is a sensible function that's relating energy intakes to mortality risk and is designed to give us that sort of U-shaped pattern that shows that avoids excess and deficiency. But for micronutrients, we need something a bit different. We need a concave function that captures the fact that there are just limits to how adequate a diet can be. And so for this, we use a simple exponential function where the health is a function of the quantity of food nutrients consumed, and it has also got some S. So the mystery S is shown here in blue, and that's a scale parameter that determines the inflection point and the curvature of the function. So we set that inflection point, you can see there in green, to be based on requirement distributions, which is the estimated average requirement plus one standard deviation. So that's the point at which 68% of the population have met their needs. And then the value 0.159 there is saying that the area under the curve to the right of that inflection point in a normal distribution, in a normal bell-shaped curve, that's the area under the curve there. So what you can imagine is that what we're saying is this is how much room there is left in that curve to reach a maximum adequacy score of 1 after that inflection point. So just to bring that to life, here's a vitamin A example. And you can see the blue lines here are adequacy for men, red lines are adequacy for women. And we can see that women's nutritional health grows a little bit faster than men's. And that's simply because they've got slightly lower requirements, and so they're slightly more efficient so-called health producers. So what happens when we apply this to Bangladeshi data? I'll get straight to the results here. First, if we look at current dietary patterns, we can see energy intakes deviate from requirements by a mean of 28%, and micronutrient adequacy is at around 50%. So it tells us there's lots of room for dietary adequacy to improve, both in terms of energy and micronutrients. Now, what happens if we optimize the food selection? Well, with the exception of a couple of nutrients, calcium and vitamin B12, almost all dietary needs are met. And since we require energy to be exactly met, that means that we've got energy deviation from needs at 0%, so perfect adequacy. And households also obtain about 98% of their recommended nutrient intakes for 11 micronutrients. Now, how do they do this? Well, they would need to buy more but cheaper food overall, particularly more fruit, vegetables, and meat, and they'd need to switch from rice to wheat flour and cut consumption of sweets and deep fried snacks. So to benefit household members, that nutrition that's been bought at the household level needs to be optimally allocated. Here we look at what happens to energy and micronutrient adequacy when we optimize only the choices and we don't change the way that households allocate the food. Compared with the observed levels of adequacy, which is that low dark green line, we can see a slight improvement in energy sufficiency, with deviation from requirements falling from 28% to 23%. But remember, the goal is to get that down to 0. On the other hand, if we look over at the graph on the right, we can see that micronutrient adequacy increases really quite a lot, increasing from 0.69 to 0.88. And so the goal is to get that right up to 1. What about the other side? Let's say we don't change the basket of foods, but we do change how that set of foods is allocated within the household. There we do see larger improvements in adequacy in terms of energy balance. So that is the bright green line. So that's showing a far lower deviation from requirements, falling down to 17%, but far smaller improvements in micronutrient adequacy. And of course, if we optimize both choice and allocation, that's the behavior change dream, then we would see those results from the first stage of perfect energy balance and almost complete micronutrient adequacy. So what can we conclude from this? The first thing I think to take home is that if households adopt pure health optimizing behavior, their nutritional needs would be almost entirely met. And all that might seem promising, but it would take really large changes in current diets that have so far proven hard to do. We don't yet know the feasibility or associated cost of achieving such changes, and we do know that there are many structural obstacles in doing so. And the second key take home is that we should not assume that women always get lower shares. And in this case, that would result in ineffective and potentially harmful design. In other places where we've seen higher gender inequities, we would obtain quite different results. And so this tells us that one gendered assumption cannot rule them all. We really need context-specific information to inform the gender sensitivity of our programs. Thank you so much. This was funded by the Wellcome Trust. And thanks again to IFPRI for sharing these data.
Okay, so Helen, thank you very much for joining us today.
Thank you.
And we'll move to the next presenter who is here with us. So Jocelyn from Cornell University.
Hi, good afternoon. Okay. So I will be presenting some work looking at farmer perspectives on food loss and waste in South India. Okay. So just to start out with some background, we know food loss and waste is a sustainability issue. It's part of the Sustainable Development Goals, specifically regarding Target 12.3, which calls to reduce food waste by half at the retail and consumer levels, and then generally reduce food losses along the supply chain. So the way that this target is measured is by two indicators along the supply chain. The first is a food loss index, and so that captures food loss from the harvest up until retail, but not including retail stages. And the second is the food waste index. So this captures food waste at the retail and consumer stages. And so what's kind of left out within these SDG indicators, or Target 12.3 indicators, is the pre-harvest stage. There's also no harmonized food loss and waste conceptual framework. And so the framework that's used for these indicators is shown on the right. And so plants and animals that are intended for food are considered when we first think about what could potentially be lost or wasted. So any plants or animals that are intended for feed or industrial use are left outside of the consideration. But as food moves through the supply chain and is diverted away from the supply chain, if they do go to an economically productive use, in this framework, it is not counted as food loss and waste because it has a productive use. So this is quite high level conceptualization and measurement of food loss and waste. But what's missing is sort of understanding the perspective of food loss and waste from different value chain actors. And there have been few qualitative studies on producers specifically and how they actually view food loss and waste. So right now, most of the data come from high and upper middle income countries. And so we sought to contribute by exploring the perceived food loss and waste pathways and decision-making among smallholder producers in South India. So we carried out this study in 10 villages in Andhra Pradesh in South India. And they were smallholder vegetable producers. We recruited them using snowball sampling, starting with existing study participants from our main study measuring food loss and waste along tomato value chains. We used semi-structured focus group discussions that covered topics including decisions to grow perishable vegetables, their production and post-harvest activities, experiences in several different food loss and waste scenarios, their strategies to reduce losses, and also considerations for future production and marketing decisions. So several themes came out from these focus group discussions. We see that there's this perception of risk or uncertainty of factors that producers do not see is under their control. There are also causes of loss that producers do perceive are modifiable. They also express decision-making based on the perceived cost benefit. And we had a final theme that was created before we started the analysis to look at the value of produce removed from the food supply chain, the perceived value. And to understand the food loss and waste pathways, we examined the circumstances and priorities that influence their decision-making. And this was used to describe feedback loops along these producer-described pathways. So I'll start by looking at the farmer to market decision-making. So all of these, this is sort of grounded in the perceptions of loss, that perceptions of loss are related to their livelihoods. And the major concerns are income losses, which is tied to this uncertainty of market rates. So one of the participants captured it really well when they said, our crop will be like a lottery for us. Sometimes if we are lucky, we will not get good benefit, or else we don't have any assurance that we may receive a good price. The farmer doesn't have faith in the rates. And this occurs as early as deciding when to harvest. So there are decision points for both harvesting and marketing when the produce is harvest ready. So the first issue is timing, and this is timing of, again, when the produce is ready for the market, but also when the market rate can be profitable. And so farmers need to make a decision about the cost and availability of labor to actually harvest the produce, and also once that is harvested, the cost of transport to bring it to a market. So one participant explained that by chance, if we harvest the crop at any cost, the stock will reach the market. After harvest, we will not keep the stock here. So if they harvest, they are absolutely going to invest additional resources to bring that produce to the market. In contrast, another participant in a different village said that we pluck tomatoes and keep for cattle as there will be a loss of transportation charges and other charges as we have to bear from our pocket. So even though they're harvested, they're not necessarily going to be transported. And these past experiences impact producer willingness to take on investment risks. And this happens both in the short term because a lot of times with perishable produce, there are multiple harvests within a given season, and so the timing can be quite close together of when things are mature enough to be harvested, and again, this timing issue of when the market rates are profitable. It can also be in the more distant or longer, medium, long term, and decisions to grow certain produce again in a different season. Next, we look at food loss and waste pathways. And the first pathway is when food quality losses lead to actual physical food loss, so the food being completely removed from the supply chain. We find that there's a range of perishability among vegetables. So, for example, tomatoes cannot be stored, whereas other vegetables, even if they're taken to the market, they can store them for another day and sell them. And these are vegetables like beans, bottle gourd, and ladyfinger that can be stored for 2 to 3 days, and we can sell them in the market. And so again, even though there's this range, it's quite short for perishables. And one of the major constraints is that producers have limited storage options. And one of the ways that they might cope with this is they might wait to harvest and hope for better market rates. So in the case of tomatoes, tomatoes will not perish even for a week. It will stay fresh on the plant. So because there's no storage, leaving on the plant is really the only option that they feel they have. And even after 1 week, if there are good rates, we will take off the waste tomatoes and take good tomatoes to the market. We will wait and watch for 15 to 20 days and see whether the rates will increase or not. And so this describes the food quality loss to physical food loss and waste pathway because of the limited storage options, having to leave tomatoes on the vine. They're continuing to ripe. Some that were ready for harvest have now passed that quality threshold and are no longer suitable, and so they end up becoming physical food loss and waste, even though they were never harvested. There's also physical food loss and waste without any changes in the quality of the produce. So producers in this area have limited market options, and the sales and rates are not guaranteed at the wholesale market. And they describe that these acceptable quality thresholds can change depending on the market rates. So even if a producer has pretty consistently produces a certain quality level, they may or may not be able to sell that at a profitable rate at the market. And this leaves producers without options when wholesalers reject certain quality grades at the wholesale market. So this looks like when the buyer buys only first class ones, as in tomatoes, he will not buy even the medium tomatoes. At that time, the wholesale owner cannot do anything. We will not get any money, and so we leave them there and come back home empty hands. The producers don't really have any other market to go to, and it would be another cost to, again, transport produce away from the market. So these are just left, and they become physical loss. So what happens when food is diverted away from the supply chain? So this is a image of tomatoes that were not sold in the market, and they're packed up in these bags to be used as animal feed. The producers most often, almost always, they don't get any money for this. They may get a very small sum if the rates are extremely high, but that's an unusual case. So there are two primary loss destinations. There's animal feed, and then it might go to trash. The producers have no perceived value in diverting vegetables to animal feed, and part of this is that investments are made in vegetable production because these vegetables are intended for human consumption. And this stands in contrast to rice, millet, and maize that serve as either human food or animal feed, depending on the context. So one participant described this as, "There's no grass now to feed cattle, so another farmer called me for giving maize. If it was tomatoes, none of them would have called me and asked me for my yield." So just a few quick conclusions. The scope of the SDG 12.3 indicators, they don't capture the food loss and waste problems perceived by smallholder vegetable producers in the context of our study. And so the main issues are excluding this food loss and waste at the pre-harvest stage, because we see that this is an area where there's a lot of opportunity for loss. Also not including food quality losses, particularly when we're thinking about perishable produce. A lot of the major food loss and waste pathways, if we think about it, they're degrading over time. That's a quality loss. And also this idea of productive non-food destinations, should they be counted as loss and should they not be counted as loss? And this matters because when we ultimately have these figures on food loss and waste, and we want to understand changes over time, who is benefiting from these measurements. So future directions, we need to expand the scope to include the pre-harvest stage when looking at food loss and waste, and incorporate food quality loss indicators into food loss and waste evaluations. And lastly, just reconsidering the food loss and waste destination criteria and thinking about, should it be a bit more broad in terms of if food is diverted away from the supply chain and it goes to any non-food use, it should count as food loss and waste. So, thank you.
Okay. So hi everyone, I'm very excited to share my work with you on temporal dietary diversity patterns and their relationships with child growth in early life in Vietnam. Next slide, please. So as we all know, it is well established that the diet quality in early life is immensely important to protect children from getting infections, being stunted, developing obesity, or having delay in cognitive development. And one common indicator of diet quality in early life is the minimum dietary diversity, which is MDD, and this is commonly measured cross-sectionally in household surveys, and a child is considered achieving MDD if she or he consume at least 5 out of 8 nutritious food groups the day before the interviews. And although cross-sectional measures of MDDs is strongly correlated with nutrition biomarkers measures of micronutrient adequacy, it has two limitations. And one of them is that because it's cross-sectional, so it cannot capture the changes in diet quality over time. So it doesn't tell us like how diet quality improve, decline, or stay the same over time. And it doesn't tell us like at what point in the early childhood that we observe the changes. And this information might be important for to designing interventions. And the second limitation is that many literature reviews have shown that MDDs do not strongly predict linear growth or weight gain outcomes, and this might have to do with the fact that growth outcomes is a reflection of the accumulation of diet over time. So cross-sectional measures might not sensitive to predict growth outcomes, and that prompt us to come up with the idea of constructing a temporal or longitudinal measures of MDD. Next slide, please. So the objective of this study is to characterize the temporal dietary diversity patterns in early life and assess the associations of these patterns with child growth in rural Vietnam. Next slide, please. So we used data from a prospective cohort of preconception micronutrient supplementation in northern Vietnam. So at baseline, we enrolled over 5,000 mothers who and randomized them into one of the three arms of the micronutrient supplementation intervention. And they will follow up until conception and delivery. And more than close to 1,600 births were recorded. And these children will follow up between for several times until they are 2 years of age. And the main data collection happened around 6 to 8 months and 23 to 25 months. But we also attempt to visit the children at several times between this period, but the sample size was much smaller. So the key challenge of this analysis is to select an appropriate sample that allow us to track diet over time, given that we have different sample size, we have a different number of children at different follow-up, and within each follow-up, the children are slightly vary in age. Next slide, please. So our strategy is to create a 4 age windows, and each window is a 3-month interval. So the four age windows are 6 to 8 months, 11 to 13, 17 to 19, and 23 to 25 months. And so we select the children who had dietary diversity data at all 4 age windows. And then we drop children without anthropometry measures and without covariate data, such as baseline socioeconomic characteristics and birth outcome. So at the end, we reached a sample size of 781. And when we take a look at the child age within each window, we found that the mean age is roughly 7 months for the first window, 13 for the second window, 18 months for the third window, and 24 months for the fourth window. But what is more important is the standard deviation, which is around 0.4 to 0.8 months. So that's so we think that this deviation is small enough that we can consider that these children are quite similar in age that allow us to proceed with analysis. Next slide, please. So in our modeling, the main exposure is the temporal dietary diversity patterns, and I'll explain later how we construct these patterns. And the three main outcomes is the relative H for AZ score, relative weight for HZ score, and relative weight for high Z score. And these relative Z scores are the standardized residuals obtained from the regression model when the Z score of the first window was regressed on the last window. And these relative Z score are the measure of the relative gain in weight or height, which is not predicted by the initial weight and height. And using these relative measures is provide more benefit than using the actual Z-score at the last window, because it allows us to control for some observed and unobserved factors at the baseline. So, and in the model, we also use covariate of socioeconomic characteristic and birth outcome data. And we use multivariate linear regression because we did not observe evidence of clustering using the intra-class correlation clustering, or ICC. Next slide, please. So in this table, it describes how we constructed temporal dietary diversity patterns. So at each window, we determine whether the child has achieved MDD, and then across the 4 windows, we track how MDD status changed. And because we have a 4 time window and 2 potential MDD status at each window, we had 16 individual trends. And then we group these trends or categorize these trends into dietary patterns based on the timing when the child first achieved MDD, and second, whether the MDD status is maintained over time. And that's how we identify the 5 patterns shown on the last column. The timely stable refers to children who achieved MDD between 6 and 8 months and maintain the MDD status over time. The timely unstable are the children who achieved MDD in the first window but was not able to maintain their MDD status over time. And then we also have, similarly, we have a delayed stable, delayed unstable, and super delayed patterns. And one key takeaway from this table is that just like about 30% of the children in our sample achieved the optimal pattern, which is timely stable. The rest of the children, they either had delay in achieving MDD, or they did not maintain the MDD over time. Next slide, please. And this table explains the result of the association between the temporal dietary diversity patterns and each of the growth outcomes. And we chose the timely stable as a reference group because we want to assess the potential consequences of deviating away from the optimal patterns. And as you see, that all values are negative, which means that potentially suboptimal patterns are associated with the slower growth. And for example, the timely, just look at the first row. Compared to children with timely stable patterns, the children with timely unstable patterns grow slower by 0.24 Z-score and gain weight and slower by 0.25 Z-score. So in short, deviation from optimal patterns is associated with slower gain in weight and height. Next slide, please. So in conclusion, from our study, in the context of rural Vietnam, we found that the delayed start of minimum diverse diet is a problem, not the delayed introduction of solid food. And also the maintenance of minimum diverse diet is also a problem. And this problem potentially associated with slower linear growth and weight gain. And the strength of this study is the new approach of using qualitative assessment of temporal patterns of dietary indicators, because it's as I walked you through just now, it is straightforward and it doesn't require any statistical assumption, and it can be potentially expanded to other indicators such as women dietary diversity or food variety score, and can be applied to populations such as school, preschool age children, adolescent, or pregnant women when theoretically diet changed during this important phase. One limitation in this study is that we did not collect unhealthy food group consumption, which is also another important aspect in this transition context in Vietnam. But I think if in the future we manage to get this data, I think it's going to be very interesting to see how and when the unhealthy food group are incorporated in the early childhood. But yeah, I think next slide, please. Yeah, just want to say thank you. Yeah.
Thank you, Cam, for the presentation. Thanks to all of you.